in the hall that was looking for someone and had to help her get where she was going. All right, we are now recording. Let me just go over. I don't know. Yeah, I think I knew yesterday that Monday that I had an appointment yesterday. That's over with. So I've got one other appointment coming up, not dealing with my eye later this month, but that's on a Tuesday, so it shouldn't bother you, but it will mess up office hours some. And then I've got another appointment with the eye doctor in another month, around July 23rd or so, though I don't think it'll be that day. But that's going to be probably a Tuesday or Thursday, or possibly even a Friday, so it shouldn't interfere with this class. And let me get the rest of you marked here. I should have done this before I turned on the recording. Anthony's here. Michael? Yeah. Marjorie's here. And Jake's here. 2, 3, 4, 5. Okay, got it. Okay. Can't think of any other announcements. We're making decent progress through Chapter 8, but Chapter 8, I don't know if I said this to you or not, but to me, this is just about the core chapter in Cal 2, okay, in my mind anyway. The next chapter will be applying, we just did applications first. That was pretty much a key too, but this is a long chapter, and like I said, it's sort of one of the keys, and then we get into sequences series and things like that. So this to me is the focus of Cal 2, in my mind anyway. So, any questions, anything we've done so far? Let me get my pen back. Okay. Now, we've done example 1, we did example 2, and if my memory's right, they skipped 3 also. We'll pick up after 3 with the other slides. So let's do this one. Example 3. What if you have the integral of cosine 4th x dx? Now, coughing all the way, okay. Lance, right? No. Cold, yeah. One off. Okay. Okay. Now, remember, let's scroll back just a little bit, down memory lane a little here. Oops, there it was, right there. We knew what to do if the power of sine was odd. Yeah, we know what to do. But if it's even, but the power of cosine is odd, yes, we know what to do. Okay? We've done examples of those two. But what if the powers of both the sine and the cosine are even and non-negative, or you don't even have one of them like this? Then we use one of these formulas. We use them as often as necessary to get to the result. Okay? So those are the ones that I consider them basically the half-angle formulas in some sense, but they call them the power-reducing formulas. They're related. So, whoops. Oops. Wait. I thought I had written something here. Oh, that was later in example 1. There it is. Okay. All right. So what do we do here? All right. Write down the integral sign. Good idea. Write it in terms of a cosine squared. So how could you write that in terms of cosine squared? Cosine squared x squared, right? dx. Now write that inner, well, let's write it here, cosine squared, okay, using that form we just showed. Let's run back and see it again. Right there. Cosine squared x is 1, well, let's say 1/2 of 1 plus cosine 2x. Got it? Okay. I'm going to pull the 1/2 outside the integral. Integral, and what goes here? 1 plus cosine 2x, but that's squared. So actually, I have to pull out a 1/4. Sorry, I should have left it in there. Okay. But you see why I have to pull out a 1/4? Because this thing is 1/2 of this, but that's in parentheses squared. So I squared the denominator and pulled it outside. Okay. Now, we have a binomial we need to expand there. How does that go? Now that 1/4 is outside all this. Expand the binomial. Anyone know how? Please say yes. 1 plus 2 cosine 2x plus cosine squared 2x dx. Got it. All right. Now, don't forget your 1/4. All right. I can start antiderivatives here for the first two terms. What would that be? X well, wait. Yep, it is right. Okay. Plus what? Cosine squared 2x. Now, is that enough? No, that's not right. That's not a polynomial. You can't do that. What's the antiderivative of cosine? Is what? Okay, decide. It is sine. Okay. Sine 2x. Is that enough? Now take derivative of sine 2x. What do you get? Cosine 2x times 2. So that's exactly what you got there. So that's correct so far. But here we got problems, Houston. Plus, I'm going to put the integral back in. Cosine squared 2x dx. What do you reckon we do with that? Second verse, same as the first. Y'all don't even know what I'm talking about there, do you? Yes, Bill Nuss, okay. And the rest of you way before you were born. Henry VIII, the song. You wouldn't know it. Okay, x plus sine 2x. Now, what will this one be? Okay, going to have a 1/2. This time it is a 1/2 because you're not squaring it. And this will be 1 plus cosine of 4x. You double it. just like we did before. Dx. All right. Now this one, finally, we can do, I think, okay. So don't forget, your 1/4 is out here in front of all that. The x plus sine 2x comes next, plus, and this 1/2 is in front of these, and what's the antiderivative of 1? X plus second. Okay, you're doing derivative of that. Okay, your antiderivative. So first, it's going to be a sine function, right? Okay, now you sort of have to unchain rule it, right? If this was a chain rule, if you're taking a derivative, it'd be multiplying by 4. Since you're antiderivative, you divide by 4. Okay. Now we sort of had that up here in this one, except we already had a 2 out front, so that's why we didn't wind up with that. Okay. And then out here we'll have our plus c. Okay, let's see if we can in some way represent our answer. I think I'm going to the top. I've got a little bit of room there. Let's multiply the 1/4 in, so that would be 1/4 x plus 1/4 sine 2x plus, now gets hairy here, 1/4 times 1/2, that's going to be 1/8 x, and 1/4 times 1/4 is plus 1/16. No. 1/8 times, that's 1/32. Yo. I forgot my other 1/2. It's 1/4 of 1/2 of 1/4. So that's 1/32 sine 4x plus c. Now there's one other thing you can do to clean up a little bit, is combine these two, and that is 3/8. 3/8 x plus 1/4 sine 2x plus 1/32 sine 4x plus c. Now, for some reason, the book likes to pull out a fraction. Now, I'm trying to remember which one they do. 1/32? No, they leave it just like that. Good for them. Okay. So that's 3/8 x. I wrote it as 3/8 times x. Okay. Plus 1/4 sine 2x. They put sine 2x over 4. Plus sine 4x over 32, just like we have, plus c. Done. Any questions on that? Now, for some reason, then they threw in something here. It says in example 3, when you evaluate the definite integral from 0 to pi halves, which they didn't tell us to do, but if you did, you would do, forget about the plus c here, and evaluate this from 0 to pi halves. Why they did that, I'm not sure, but they did. All right, when you put a pi halves in, 3/8 of pi halves will be 3/16 pi. Right? Believe it or not, that's the hard part. Now when you put in pi halves here, Yeah. Does anyone else come in? Oh, I wasn't looking. Okay. Now, evaluating this from 0 to pi halves for some reason, okay? The 3/8 times that is 3/16 pi. You put pi halves in for x. 2 times pi halves is easy. Pi. And sine of pi is 0. Okay, so that's 0. You put in x pi halves for x. 4 times pi halves is 2 pi. And sine of 2 pi is 0. And you put in 0 here, and that's 0. Put in 0 here, and that's 0. And put in 0 there, and that's 0. So basically there's your answer. 3 pi over 16. Lots and lots and lots of zeros there. And they note here says the only term that contributes to the solution was the very first one, 3/8 x. And that observation was generalized in the following formula by a guy named John Wallis, who preceded Newton, and actually, if I'm not mistaken, he may have also been at Oxford. I think he was, or Cambridge, I think it was, whichever school Newton was at. I think he was there before him, maybe even overlapped a little bit, okay? And he, they say, influenced his thinking of both Newton and Leibniz, okay? He was credited with introducing the present symbol for infinity. I didn't know that before I read it here, okay? So here are Wallis's formula. Let's see, are these going to show up? Let me see. They may show up in the slideshow. Let me see. Anyone need this any longer? Okay. Let me see. No. Oh, here they are. Yeah, there they are. Yeah, I skipped right past them. Okay, here's Wallis's formula. If n is odd, and you got cosine, okay, odd and greater than 3. Now what they don't say here, and I think they should have said, n is an odd integer greater than 3, okay? It's just, yeah, well, I guess when you say odd, you imply integer, okay. Greater than or equal to 3. Then if you're integrating just from 0 to pi halves of a cosine to the nth x, where this is an odd number, okay, then your that integral is going to be 2/3 times 5/4 times 7/6 all the way up to n minus okay, yeah, okay. You don't have a pi in this one. This one you do, okay? And you just keep going through this process. You start at 2/3 in because this has to be greater than or equal to 3. So when it's equal to 3, 3 minus 1, and then the n is odd. So the next one, if this n would have been a 5, then it would have been 5 over n minus 1. If it had been 7, then 7 over n minus 1. And you keep going and multiplying these factors together until you get to whatever your n is. 15, 14 times over 15. And you're multiplying all these together. Okay. That's the first of his formulas. The second one, if n is even, and you're doing cosine that way, and this again is n is 2 or more, okay, even energy. So see, the only thing excluded here is n equal 1. You can just do that without any of this. But do this for here. Now you got that pi halves in. I'm going to say you got to have a pi in it if it's even, and this on the side. And then you do the same thing. The first even integer is 2. 2 minus 1 is 1. Next even integer 4 minus 1 is 3. 6 minus 1 is 5. All the way up to whatever your n was, 14. That would be 13 14ths. And then multiply that by pi halves. These formulas are also valid when cosine nx is replaced by sine to the nx. Okay? For some reason I would have thought they would have flipped and had the pi with the other one, but I guess they don't. I guess it's still valid there. Well, of course it would be. Because if you're integrating from 0 to pi halves, sine function goes like this, cosine goes like that. 0 to pi halves, that's the same area. So yeah, they would be exactly the same. Make sense? Now this is only if it's going 0 to pi halves. Always positive for both of those. All right, now we're ready for, on page 535, integrals involving powers of secant and tangent. Okay? And these guidelines will help you in these regards. Okay? We have the integrals of secant to the nth, tangent to the nth, dx. Okay? Now, when the power of secant is even, now remember when we started off with sines and cosines, we started with odd powers. Those were our favorites. Now, we want the power of secant to be even and positive. Save the secant squared factor and convert the remaining factors to tangents. Okay? So, secant is even, like secant to the 6th power. Pull out once secant squared. Getting it with the dx. That leaves you secant to the 4th, which is secant squared squared, and take that secant squared and convert it with the Pythagorean identity to tangents. Then expand and integrate there. Okay? So here's what we've got. And the power of secant is even and positive. So if it's even and positive, you can rewrite it as 2 times k. Because if it's even, it's 2 times some number k. Okay? Tangent can be anything. Who cares? Okay? Now, pull out one of those, secant squared, and now you'll have secant squared left here. Okay? They've done it rather strangely, but if you pull out a secant squared, this will be a secant of 2k minus 2, right? But you took out 2 here. Okay? And 2k minus 2 would be 2 times k minus 1. So you put the 2 on the inside and the k minus 1 on the outside here. Leave the tangent alone. Okay? Now, this secant squared, anyone remember the Pythagorean identity for secant squared? 1 plus tangent squared. So put in 1 plus, you read well. Good. Okay. 1 plus tangent squared here. Raise it to that power. Doable, maybe messy, but doable. Your tangent's still there, and your secant squared is still here. Now, why did we leave the secant squared? You got everything else in terms of tangent? The derivative of tangent is secant squared. This is your du, so to speak. Okay? And so, go to town with that there. Okay? So, expand this, multiply through by this, distribute this back inside, and then that will be everything in terms of tangent, and this is a d tangent. U, du. Okay. When the power of tangent is odd and positive, save a secant tangent factor and convert the remaining factors to secants. Okay? Then expand and integrate. So your tangent now is odd, okay? Now if your secant was even, you don't even have to go through this. But if the secant is odd, the tangent is odd, Then expand this, pull out one tangent there, pull out one secant from here, okay? So that leaves you M minus 1 secants here, and this gives you, if you pulled out one, you just have 2k here. We'll keep the 2 with the tangent x and the k on the outside of that, okay? Now this is, what is tangent squared? Secant squared minus 1, okay? You read well, okay. So you have a secant to the M minus 1 from here. A tangent squared, k, well this is secant squared, so take this, expand that. It could be messy if k is very big, but it's all doable. Pascal's triangle helps, okay? You have to keep up with the signs on that one, okay? And then you have a secant tangent here. You pulled one of the secants here, one tangent from here. Why did we pull out a secant tangent? That's the derivative of secant, exactly. So this would be in terms of powers of u. All these are powers of secants, okay? That's your u, secant x, and this is your du, secant x tangent x. That's a power form, okay? Now, notice what they did not include. This is for any even secant, no matter what the power of tangent is. If secant is odd, then tangent has to be odd, okay? But they didn't say what happens if secant is odd and tangent is even. That's a problem, okay? They haven't gone into that one here. So we probably won't be doing that one, okay? Well, and let's see, wait. Here's what happens, okay? When there are no secant factors and the power of tangent is even, so this is what I was talking about before, and positive, convert the tangent squared factor to a secant squared factor, and then expand as necessary, okay? So what does that mean? Your no secant and tangent's even, then pull out one tangent squared, okay? Because that's the derivative of secant. No, I'm sorry. Convert this to secants, okay? Have they done this one right? Seems like to me okay, what this gives you is what they call a regression formula. You just keep doing it, wearing this down, wearing it down, because every time you pull out 2, it's going to be even, but you get in terms of secant. So you just keep going. We'll get to that in a minute. Now, when it's of this form, secant m, where m is odd. That was the problem before. In positive, you use integration by parts. One secant here and the rest of them there. Then you have even secants for the rest of them. You can do the one secant. When the first 4 guidelines do not apply, try converting the sines and cosines and see what you can come up with. Okay. They can get a little messier here, as we will see. Okay. So let's do this one. Now notice when they said tangent or secant, what it had to be integers, odd or even. Remember, they didn't say the other one had to even be an integer, okay? And this one it's not. What would be the first thing you would do to this problem? I don't know if you would do it. I would do it. Get it out of the denominator, you said? Okay. How would you do that? Secant to the minus 1/2 x I like it. Okay? Now, what do you do with that? Which way do you think you're going to wind up going with this? Okay, pull out a tangent. Okay, so this is going to be the integral. I'm going to put it over here. Tangent x. That left you a tangent squared x here, right? What do you do with secant? Pull out one of there too. You want a secant over here. Does anyone know why we want a secant x there? Because that's the derivative of secant. Now what would that leave us here? Secant to the negative 3/2. Okay, because those have to add to be what you had to begin with. Secant to the 2/2 was secant to the negative 3/2 was secant to the negative 1/2. Okay. Now, this is a d secant, right? That's in secants. You just need to get the tangent in terms of secant. And what would that be? Say again? Oh, you should. Tangent squared in terms of secant squared. Say that again. Secant squared minus 1. Get to know your Pythagorean identities. They're your friends here, folks. Big friends. Okay? And that's going to be times secant to the minus 3/2 x. And then you have a, I'm going to reverse the order just because I like to, secant x tangent x dx. Okay? Now, what might you do with that? Oh, well, we got one more step we know we're going to do. What's that? Distribute just the secant into that. What would this give you? Maybe it's harder than I thought. Anybody? Secant to the what? Okay. When you're multiplying same base, different exponents, keep the base, add the exponents. 2 plus the negative 3/2 is positive 1/2. Okay? Minus, and this one obviously is secant to the minus 3/2 x, and that's times secant x tangent x dx. All right, what would you do at this phase? I was going to say, I was going to bet what Marjorie was going to say when she had to say it.
Substitution.
Oh, yes, I thought maybe she would say that. What would be your substitution? Okay. What seems to show up there a lot? Secant. Let's let that. Let u equal secant x. Then, what's the next step? du is equal to, guess what? Anybody? I can't hear.
Tangent squared.
No, you're doing backwards. Derivative of tangent is secant squared. Derivative of secant is, that's why we did it. Secant tangent. Strange but true. Okay. Let's see. I don't see many with books, but you got a book somewhere, I hope, okay? Derivative of secant is secant u tangent, this is of u's, secant u tangent u, du, okay? So, that is why we did that. So let's rewrite in terms of our integral. What's your first term there? U to the 1/2 minus u to the negative 3/2 du. That's it, folks. That's all. Done. Except integrating it. And how does the first one integrate? U to, 2/3 u to the 3/2. I usually do the 3/2 first, adding by 1, then multiplying by the reciprocal. Okay, I'll let you go next. Okay, it's going to be u to the negative 1/2 power. So then you're going to be multiplying by a negative 2, and you had a negative 1, so that's going to be plus 2. See it? Okay, and one last step. Plus c, because it's an indefinite integral. Okay? Well, that wasn't the last step. You started out in x, you need to wind up in x. So what will this be? If u is equal to secant x, guess what x is? Now that's the problem. We haven't really talked about inverse secants, have we? Oh, we don't need that. We just need to plug this in. Yeah, okay, never mind. If u is secant x, just plug it in. That's equal to 2/3 secant to the 3/2 x plus 2, get out of there, okay, plus 2, you can write it to the negative 1/2 or 1/2 or whatever. I think I'd just assume this way, secant to the 1/2. Or you can leave it as negative 2/3. I don't really care. And then plus c. How did the book get out of there? Okay. They left it as negative 1/2. Okay. 2/3 secant to the 3/2. And they put the 3/2 on the outside. I like to write it next to secant. It doesn't matter which way you do. Plus 2 times secant x to the minus 1/2. You know, just plugging in the u there. Plus c. Not really that bad. All right. You know, oh, let's see how they did it. It's pretty close to the same way I think we did it. Anyone need me to leave it up there a little bit longer? Oh yeah, some are still writing. I don't think I covered anything there, did I? That's not covered anything. Is this making sense? Okay. Everybody got it? Okay. So let's erase all that. And let's see how they proceed. Because you expect to use the power rule, they jump right into it with u equals secant x. Yeah! Did I see that coming? Well, you almost have to. The most complicated part. And that's obviously secant. So we need to head that direction. Okay? You have to use as your d part, the part that you're going to change, something that has the integral power. Okay? So that means you're going to be changing the tangent x. So u has to be the thing you're blending toward. So you save a factor of secant x tangent x because that is your derivative of u, du. Convert the remaining tangent factors to secant so you have everything else in terms of your u secant. Okay? So they rewrote as we did, but they put it in front, secant to the minus 1/2, and they like to put it on the outside, which is fine, times tangent. Then they put the tangents cubed on the inside. Well, why don't you be consistent, you know, but they put tangent cube here, that's why I put secant to the minus 1/2 there. But I guess they're afraid you may be confusing it with inverse secant, which I just about did. Okay? All right. All right, they did the same thing we did. Because they're going to change this to d secant, we want secant x tangent x. So we need to take 1 away from this, leaving there's a minus 3/2 here, because they pulled the positive 2/2 out. Pull out one of those, leaving us a tangent squared. Okay? That's all right, because this is directly reducible to secant squared. Okay? Using your Pythagorean identity. So that then becomes the integral of secant to the minus 3/2 times tangent squared of secant squared minus 1 times your d secant, which is secant x tangent x dx. Leave that alone, okay, for now. Then when you distribute across, this is to the minus 3/2, this is to the 4/2, that's going to be secant to the 1/2, and then this is to the minus 3/2, and then there's your d secant. Leave that alone, okay. And then, they don't bother with the u substitution, okay? They say, this is d secant, and these are all secant, so just do your anti-derivatives with secants. Basically, think of them as u's, okay? So this will be secant to the 3/2, which means you multiply by 2/3, minus secant to the minus 1/2, which means you multiply by minus 2, which makes that minus a plus, and then that's plus c. So you got directly there doing all that, but I found that students in general, and most of the time I like to do the substitution to make sure I don't screw something up and trying to skip too many steps. Okay. Any questions on that? Example 4. Okay, I turned the page and didn't realize it. All right, they're skipping to involving sine and cosine products. We're not there yet. We got to do 5, 6, and 7. All right, I don't think I can go on. Okay, so let's do example 5. Find the integral of secant 4 3x tangent cubed 3x dx. All right. This one is sort of an optional one. You can go either of two ways. Which way would you like to go? Not home. Okay. Okay, I like that idea. That means you're aiming toward getting everything else in terms of tangent. So why pull out a secant squared? It's the derivative of tangent, right? That's why we want to pull it out. Okay, so if you pull out a secant squared, that leaves you a secant squared 3x. And then this is a tangent cubed 3x. And this is a secant squared, that's the one you pulled out, x dx. There's a reason for that. All right, trying to get everything in terms of tangent. That's why you pulled out a secant squared, because that's the derivative of tangent. So what is secant squared in terms of tangents? Second? Tangent squared plus 1. Tangent squared plus 1, x plus 3x, sorry, 3x plus 1 times tangent cubed 3x, and that is a 3x there too, by the way. Okay, sorry about that. Tangent, okay, and then let's leave it as a secant squared 3x dx. because I know what, okay. Let's multiply through, distribute through, and what do we get? Integral of tangent to the fifth x, 3x, I keep saying x, 3x, plus tangent cubed 3x times secant squared 3x dx. All right. Now, what might we choose to do? You want to do a u substitution? Is that what you said? Okay. Let, and what do you want it to substitute as? U equal tangent what? 3x. Okay, then, next line, du is equal to secant squared 3x times 3 dx. You have to chain rule that. Remember? Can't avoid it. And that's not what you got. You got this part, so we are going to need to divide out by 3, right? So let's divide both of those by 3. Okay. And then this is your du over 3. So what we're going to do is pull out that 1 over 3 times the integral of, what would the first one be? U to the fifth plus u cubed du. The 1 over 3 is out front. I think even I probably could do that one. What would that be? Help me. U to the 6 over what? Over 6. U to the 4th over 4. And then we're going to have a plus c, but we won't worry about that until later. So let's go on and multiply through and substitute back in. That would be 1/18 tangent 3x, tangent to the 6th 3x, plus 1/12 tangent to the 4th 3x plus c. Now, whether they write it that same way or yeah, well, they just put it over. I'm sorry. Tangent to the 4th, and they reverse the order too, okay? Because they wrote it differently, okay. Tangent to the 4th, 3x over 12, plus tangent to the 6th, 3x over 18, plus c. Same answer. But see, again, if you were doing this in WebAssign, even though that's a perfectly correct answer, if they wanted it in different order and over the denominators, they're going to say it's a wrong answer just because it's not in the form they were looking for. Because computers basically are stupid. They're only looking for one thing. Their intelligence is totally artificial. No, that's something else. Okay. All right. Any questions on that? Do you need it a little longer? All right, let's delete that then and go to example 6. No, that was 6. Well, no, that was 5. Example 6. And this is one with a definite integral. Integral from 0 to pi fourths, tangent 4th x, dx. Okay, what in the world can we do with that? Any ideas? Second? Okay, let's see if by parts work. I believe that was the secant M was the one that said do it by parts. When tangent was even and positive, it says convert it to a secant squared factor and then expand and repeat as necessary. So we need to take this and convert it to secant, or at least one of them to secant. Okay? So let's, but the rule says when it's of this form, no secant factors and power of tangent is even and positive, convert the tangent squared factor to a secant squared factor, expand and repeat as necessary. Okay? So what they mean by that is integrate from 0 to pi fourths, okay, and this will be exactly what I said to do. I'm writing the other thing. Okay, this will be, well, that was okay. Tangent squared x squared dx. Okay, that was pretty simple, right? Let's convert that tangent squared to a secant squared. Integral from 0 to pi fourths. And what is tangent squared in terms of secant squared? Say that again. Secant squared x minus 1 squared dx. Okay? Now, feel the sneeze coming out. All right. That will be the integral from 0 to pi fourths. And expand that binomial. Secant fourth x minus 2 secant squared x plus 1 dx. Now, this goes back to our guideline 1 then, where you have secant being even, whatever tangent is, okay? And what was the rule there? Okay. Well, yeah. Remember this last one here we can do separately. So, I don't know, let me not just say that, let me write it, okay? And can you do that automatically, or do I need to write it down? Integral of dx from 0 to pi fourths. What? You want me to write it down? I want you to tell me what to write down. Integral of dx from 0 to pi fourths. I'll write it down. Because it's just 1 dx. I pulled that one out. Think we can do that one, can't we? What is it? Pi fourths. This is just pi fourths. Because it's x, okay? Evaluated from 0 to pi fourths is pi fourths. So this is going to be at the end there somewhere. Now we've got to do our secants to the fourth, okay? Now, it feels like we're running in circles almost on this one, okay? So this first is going to be 0 to pi fourths, okay? And this is going to be, pull out a secant squared, Okay, there's that first one, right? Okay. Minus 2, but can we do this one? 0 to pi fourths secant squared x dx. Please say yes.
Yeah.
How? Antiderivative of secant squared. Tangent, exactly. Okay, so this we can evaluate. This is just going to be a minus 2 tangent x evaluated from 0 to pi fourths. Okay, and then we got our pi fourths out here from the last term. That's a fourth. Okay, for some reason it's not showing up well. Okay, so we'll come back and do that in a minute. This one, we're going to write 0 to pi fourths. Now this one, secant squared, we're going to write it in terms of tangent squareds. And what's that going to be? What is secant? Second?
Tangent squared plus 1.
Tangent squared plus 1? Okay, and then we're going to leave this secant squared alone. Why do we leave it alone? What's that actually? Secant squared x dx. Derivative of tangent. And this is in tangents. Okay? So I'm going to go to the top and try to finish this. This will be the integral from 0 to pi fourths how might we, I'll write it down. Tangent squared x secant squared x dx plus the integral from 0 to pi fourths of secant squared x dx. Okay, see what I've done there? Minus, and let's go on and evaluate this one. I'll write down the 2. What is tangent of pi fourths? 1. Okay, minus the tangent of 0. 0. So that's just going to be what? So it's a minus 2 plus pi fourths. Okay? Continue. Now, what might we try here? If you don't know what it is automatically, let u equal tangent square or tangent x, then du is equal to derivative of tangent x. We haven't done it much today, have we? Say again? Secant squared. Secant squared. That's why we pulled it out, remember? dx. So what is our integral here? Get out of there. Okay. I'm rapidly running out of room. I think I'll start erasing down below here. Is that okay? We've already dealt with this. I think we've got our answers. It takes a long time to erase because there's so much on the screen and it gets lost in its pixels, I think. Whoa! I didn't mean to do that, but I've done it now, so I'm going to pretend it wasn't there. Okay. So what's this integral? This is coming down to here. Leave off the units for now. Just fill in the u's. What would that be? U squared du. Okay. Now, do you want to fill in the limits, you might say, the values here? Okay. When x is equal to 0, what is u? 0. When x is equal to pi fourths, what's u? 1. Okay, that's pretty nice, isn't it? Okay, so that's that one. We'll come back and do that in a second. Let's do this next one, plus, oh, have we been here before? Antiderivative of secant squared? Say again? Tangent. Tangent x evaluated from 0 to pi fourths. Now last time it was a minus 2, so don't think those are just going to, good. And then these was minus 2 plus pi fourths. We've already evaluated those, so don't reinvent the wheel. All right, so what's this one? Pretty simple integral. Say again? 1? Oh, you're already evaluating it. It's not quite right. Antiderivative of u squared. U cubed over 3. That's evaluated from 0 to 1. We'll come back and do that in a minute. Let's do this evaluation. Plus, what's tangent pi fourths? Minus tangent 0? 0. Minus 2 plus pi fourths. Okay? I can see one thing that will simplify, but what do you have in that first one? When u is equal to 1, you have 1/3. And when you combine these two, it'll be minus 1 plus pi fourths. I think. I sure hope. So this is going to be minus, get out of there, minus 2/3 plus pi fourths. That is such a strange answer. It doesn't seem like it can be true. Pi fourths is just a little bit more than 3/4, and 2/3 is a little bit less than that. So you're going to have a pretty small fraction there. Is that all she wrote? It seems like it, for some reason in the book they didn't evaluate 1/3 minus 1. I did. Someone plug that in your calculator. Negative 2/3 plus 1/4. Pi fourths. Pretty small decimal. Not tiny, but pretty small. That's what they got. Approximately 0.119. Yep, good deal. Now, why is that the case? Well, what were you integrating in the beginning with? Tangent to the fourth. Well, tangent to the fourth, if you picture this, they do it in the book, but it's not too hard. I just don't have much room to picture it. A tangent function itself looks like this, right? Where it's going to infinity at pi halves, okay? But when you raise it to the fourth power, you steepen this, flatten this, and steepen this. Now you're only going from 0 to pi fourths, and for a long way there's not a lot under there, and then finally here where you get the pi fourths, there's a little bit, so you've got a really small area in there, an incredibly small area, and no wonder that's because it's pretty narrow this way, and since it's so flat there before it starts going up, it's only after the pi fourths does it go up rapidly. It's still pretty narrow there, so not surprising it's a pretty small number. They say try using the midpoint rule to approximate the integral. If you really want to do it, knock yourself out. It said with n equal 15. I'm not about to do the midpoint rule for n equal 15. Not now, okay. Now, example 7 is sort of a pain. Well, I shouldn't say that. I don't want to bias you, okay? But it's preceded by something that's sort of a pain, okay? For integrals involving powers of cotangents and cosecants, you can follow a strategy similar to that for powers of tangents and secants. Also, when integrating trigonometric functions, remember it sometimes helps to convert the entire integrand to powers of sines and cosines. So let's see if this might be an example of that. Example 7. Find the integral of secant x over tangent squared x dx. Okay. Now, my first approach to this would be the problem child is this tangent in the denominator, right? So I want to do it in terms of tangent. Well, the derivative of tangent is secant squared. We don't even have a secant squared in the problem. So that's going to be problematic. So rather than fight and sweat and curse and all sorts of things like this, let's just change everything to sines and cosines and see if something else good happens. Anything good happens. What is secant in terms of sines and cosine? What is secant? 1 over cosine. And what is tangent in terms of sines and cosines? Sine over cosine. But this is in the denominator, so this will be a sine squared x over a cosine squared x. Agreed or not? You okay with it? And then comes your dx. All right, now what's the first obvious thing you see? You can lose a cosine. Okay. Now, what do we have now? Let me rewrite it in case that's a little confusing to you. The integral of cosine x over sine squared x dx. What would be one thing that would sort of come to mind?
It could be tangent times cosecant.
Okay, you say it's tangent times cosecant? Probably is. No, it would be over tangent. Right? Cosecant over tangent, which may be true, but now you're going back to something that's missing. Okay? Sines and cosines usually are easier to deal with. Okay? Now, what's the problem child of that? The denominator, right? So let's let that be our u. I was sure that you were going to come up with this, okay? All right, so let's let u equal sine x. Boy, my screen is a lot like me. It's wanting to lie down. Okay, let me pull it back up here. Okay, then what's next? Second? du is equal to? Second? Anybody? Cosine x. What else? dx. Ding, ding, ding. That's our numerator. So what do we have here? The integral of is du over u squared, which I don't really like too much, so I'm going to rewrite how. U to the negative 2 du, and I think even I can probably integrate that. What would that be? Negative u to the minus 1. That's right. Which would be negative 1 over u. Right? And what's u? What's u? Negative 1 over sine x, which is negative cosecant x. Now who would have, oh, other thing, plus C. Okay, don't forget your plus C. Could it be? Oh, yes it is. Okay. If it fits one of the patterns they showed us, your guidelines, that kind of stuff, go with it. But if you can't get it to fit one of those nicely, try getting in terms of sines and cosines. See if that'll help. If it does, great. If it doesn't, look it up in a table, try numerical integration, something else. But you basically expended most of your tools, and you have to go to something else. Any questions? All right. So now I think we're ready for integrals involving sine, cosine products. Now, didn't it sort of feel like we had that before? But what we had before was powers, not just products. This time, no powers involved, just products. Okay? Now, I don't know if any of you remember these wonderful little things here. If they involve products of sines and cosines of two different angles, they occur in many applications. I just can't think of many, okay, but I guess they must. In such instances, you can use the following product to sum formulas. And I can remember teaching this in trig and saying, you'll seldom run into this, but here they are if you need them. Now, does anyone recall where these came about? Now, they did leave out one. No, they're okay. Because this can be written either way. Okay. Anyone remember how these come about? You have to go way back to your, basically this is the giveaway, your sum and difference formulas. Okay? And fiddle around with them, manipulate them, eliminate things and stuff, and you come up with this. Okay? So if I ever really needed this, that's probably where I would go. More likely look it up in a table somewhere, because I'm not going to remember. I'm not going to memorize that. I don't memorize well, so I'm sure not going to try to memorize that. Because there's too many places where you get sign wrong and out of order and stuff and just get it totally wrong. But write it down somewhere, get it in a table, and if all else fails, you can go back and get it from your sum and difference formula for sines and cosines. So here they are. Use them as necessary. Okay? Now, do I say memorize them? I wouldn't, but that's up to you. If you're a good memorizer, go for it, folks. Okay. So here's example 8. Find sine, the integral of sine 5x cosine 4x dx. There's no substitution. There's no trig substitution. There's nothing I can think of to do that except those formulas. When are you ever going to run into integrals like that? I don't know. You might. It sort of smells a little bit like Fourier analysis, but not getting into that in this course. Okay. So let's go back here and see which one of these we want. It was a sine cosine. That's that middle one right there. Okay. So let's write down what that is. That would equal 1/2 the integral. Go back. Sine of the difference of those two x. So that would be sine of 5 minus 4 is 1. So that would be sine x. Okay. Plus, I pulled my 1/2 out, and I was going to point this out, and I forgot to. Notice here they have grouping symbols and grouping symbols and grouping symbols. Now, when I do these, I used to always do parentheses, then brackets, then braces, and then you can see them. This book doesn't like doing braces, and maybe people don't do braces anymore. I know in computer programming, everything's a parentheses, and those are really hard to keep up with all those. So I would like braces. If I were doing it, this would have a brace, and there would be the accompanying brace. Because those are your parentheses, those are your brackets, these are your parentheses, those are your bracket. That would be my braces, okay? Or this one, this one we're working on. So that's why I pulled the 1/2 out, because it's outside of all of that. So that's why it's outside the integral, okay? Meant to point that out to you, okay? Plus, oh, left off the next part, plus the sign of the sum of the two. And what's the sum of those two? 9x. I guess I'll put those in parentheses, dx. Now I think maybe even I could do that, but let me get you to do it for me. Second?
Are you going to split them?
Yeah. But I wasn't going to physically do it. I was just going to do it one at a time. So what would the first one be? Is that right? Next. Okay. Ask the question, change your sign. Okay. Next. Negative. Second, cosine. Second, 9x over 9. Okay, I was going to put the 1/9 here. It doesn't matter how you do it. And then you have your plus c. Okay, so this will be minus cosine x over 2 minus cosine 9x over 18 plus c. Now, that's how they wrote it last time, and that's how they do it this time too. I wasn't sure they were going to be consistent. Okay. Now that was my scratch. I think theirs is going to follow it almost directly, exactly. Let's see. Consider writing the second product to some formula. That's what we did. You can then have the first one be 1/2, pull it outside, and they skip steps like, well, we did too, I guess. Sine x plus sine 9x dx, and that's 1/2 of negative cosine minus cosine 9x over 9 plus c, which is negative cosine over 2 minus cosine 9x over 18 plus c. Done. Now, that's the last, okay. The bottom of that page, it says to learn more about integrals involving sine cosine products with different angles, see the article Integrals of Sine Products of Sine and Cosine Angles with Different Arguments. Clever, okay? By Sherry, J. Nicole in the College Mathematics Journal. And they have a site you can go to. So if you wanted that to be your paper topic, you certainly, they give you a source right there. The book is great for ideas. It can't be your source, but it can give you the ideas. That can be your source. Homework exercise 8.3. Any of the odds 8 through 13, they're all at Calc Chat. 7's at Calc View. Any of the odds 15 to 19, they're all at Calc Chat. Any of the odds 21 to 33, they're all at Calc Chat. 27's at Calc View. Either 35 or 37, they're both at Calc Chat. 39's at Calc Chat. They like putting these slope fields in there. They're sometimes called, there's another name for them. Seems like they're sometimes called direction fields or something like that. Another one, 41, is at Calc Chat. Any of the odds 43 to 47, they're all at Calc Chat. 43's at Calc View. 49 to 57, all at Calc Chat. 59 to 65, all at Calc Chat. 61's at Calc View. And then you can explore doing 67 is at Calc Chat, and or 69 is at Calc Chat. 71's at Calc Chat. 73's at Calc Chat. 79's at 5's at Calc Chat, and 77's at Calc Chat. You do either 79 or 81, they're both at Calc Chat. 83 or 85, they're both at Calc Chat. Going back to Wallace's formula, 87. And of course you could write Wallace if that's what you're interested in. And there that said the Fourier series, and their Fourier series shows up. There's another potential paper topic. Fourier, or his series, or how did he develop his series, or what are his series used for, all sorts of things like this. They also mention the section project. They go back to Wallace a little bit and talk about the Wallace project. A formula for pi as an infinite product was derived by plain John Wallace, 1655. And there's pretty interesting application of it there. And there's for further information, you have another math article there you could use. All right, any questions? Let's move out of 8.3 and go into 8.4. Now, how are we doing time-wise? We're just about halfway through the class, very close to that. Anyone need a break, potty break, bladder break, stretch break, snack break? Anyone just move around? Okay, let's do it. We'll pick up here when we come back in 8.4. Okay, I'll put this on hold for now. A minute or two early today. I won't need many, but I just need a little bit to run down, because I have to go to the bathroom. I can't do it like this. I get it all over my face, so I have to be in front of the mirror, and I still get it all over my face, but at least a little less. All right, Chapter 8 continues on integration techniques, and we ultimately will get improper integrals, so we're not really going to do that much with them. Now we're going to do trigonometric substitution. Now wait, didn't we just do that? No, we were doing trigonometric integration, okay? Not trigonometric substitution. So this is a little different from the last, and it differs from regular substitution in a certain way too, and I'll wait till we get the slides up there and point that out to you. So what were our objectives here are to use trigonometric substitution to find an integral. That's what we're doing. And we'll use integrals to model and solve some real-life type applications. They always say that, or quite often. So, we can use trigonometric substitution to find integrals that involve certain radicals. A radical of this nature, where you have some constant minus the square of a number, of a variable or function or expression, a square of a constant, plus, this is the square root of a constant, minus, this is the square root of a constant, plus a square of a function, or the square root of a function minus is sort of the reverse of this one, minus the some constant, okay? Now the objective here with trig substitution, okay, now time out just for a moment. These radicals could occur in a numerator, in a denominator, or somewhere else. Now, if somewhere else in the problem there happened to be a u or a 2u, say in the numerator, especially in the numerator or somewhere, then these are no problem. You do a straight substitution. Not u substitution, some sort of substitution here to do those. But if you don't have that u or 2u with a du somewhere out there, there's no way to do this. So you need a substitution, but not our normal substitution. So the objective with the trigonometric substitution is to eliminate the radical in the integrand. To do this, you use these Pythagorean identities. Boy, have we seen these before, okay? Now, cosine squared theta is 1 minus sine squared theta. Hint, take a look at this, okay? Something minus something squared inside a radical, that means this thing represents something like a cosine. Or secant theta is 1 plus tangent squared theta. Secant squared theta is 1 plus tangent squared theta. Bingo, like this. 1 plus u squared. And that's the square root. That would be, this is where these come from. Okay, now, the thing that's a little, on this one with the plus, doesn't matter which order you do it. So don't think just because you u squared plus a squared, it's the same thing. Just like tangent squared plus 1. So it doesn't matter. Okay? And then the other one, tangent squared theta, is secant squared theta minus 1. Look how similar that is. Function squared minus some constant, square root of that. This is it. These give away how you do this. For something that looks like this, use a sign substitution. Something that looks like this, a tangent substitution. Something that looks like this, a secant substitution. That's the whole point. That's the whole section here is basically given away in just that. Now, but that's not all. Well, okay. For example, for A positive, which is usually a pretty good thing to have, let U equal A sine theta. Okay? Remember, the A is this form here. This is the form we're going to do our sign substitution in. So if A being positive, let U equal A sine theta. So then what I would do here are a couple of steps. U squared, since that's how it shows up here, would be A squared sine squared theta, right? So plug that in here. A squared from here minus, and then square this, A squared sine squared theta. Factor out the A squared, okay? And that gives you A squared times 1 minus sine squared theta. Well, this is, I would take this right out of here. If that's an A squared, take it out of the square root and put the A in front, and then 1 minus sine squared is cosine squared, and the square root of cosine squared is cosine. So there you've eliminated your square root. Okay, now, they also put this in here, where theta is between minus pi halves and pi halves. Anyone think of why they might have that in there?
It keeps it from being negative.
Okay. Actually, yeah, because ultimately what your substitution is going to produce is this, and there cosine is positive, from minus pi halves to pi halves. If you start adding those parts, then they're going to negate, okay, and wipe out. Notice that cosine theta is greater than 0 in this range. Yeah. So I didn't realize they were saying down there. All right. Now, that's not the only thing they do. We also draw little triangles. Every time you go to make one of these substitutions, like we just did there, let U equal A sine theta. As soon or very soon after I do that, I then draw me a little triangle. We love little triangles, don't we? They're so helpful. Okay? Draw you a little triangle. All it has to be is a right triangle. It doesn't have to be very pretty. You don't have to have the dimensions correlating to anything. Just draw it. Okay? Identify the theta. That's usually a good one. Okay? There's your right angle. If you couldn't tell, that was supposed to be the right angle. Okay? As soon as you identify that as theta, then sine theta is going to be, well, maybe do this first. Divide both sides by A. And sine theta is U over A. So this must be U, which is the opposite, over A, the hypotenuse. Okay? Every one of these substitutions, draw your little triangle, and when you have identified what your substitution is going to be, draw it in like this. You will find this unbelievably helpful later on. Okay? Perhaps several times in the problem, this will be helpful to you. So that's what they're showing here. When you have this and that kind of form, you're going to use U is equal to A sine theta. Rewrite that as sine theta is U over A. Put your theta in there, U over A. Well, guess what? Guess what? what is this remaining side down here? Anybody?
Square root of a squared.
The square root of
A squared.
a squared minus u squared, which is exactly what this is, isn't it? Oh my goodness. Isn't this a pretty little package that we have here? Now, then from this thing right here is a cosine theta, which we just got doing this way. You can also see it this way, because cosine theta is adjacent over hypotenuse, which is this over that, multiplied by a, and you've got that. And that's good for negative pi halves and pi halves. Okay. Same thing here. If you have a square root of any constant, because any constant, as long as this is a positive, of course. If it's not a positive, you go down here, you know. But if that is positive, then take the square root of it, and that may be square root of 17/3 or whatever. You can still take the square root of it and make it an a squared. And you have this plus u squared. This is your tangent substitution. Let u, now notice the difference here. Before, we let the u be the complicated part here. Now we're letting u be the substitution, be a trig thing instead of the u, which is part of the problem to begin with. Okay? So that's a little bit different. It almost seems backward from our other substitution because it sort of is. So if u is equal to a tangent theta, draw your little triangle. There's your angle theta. The tangent of theta is opposite over adjacent. Well, divide by a, that makes that the u, that the a. Opposite over adjacent. Divide by a. Then, what's the side here? The hypotenuse? The square root of a squared plus u squared, which is exactly what you're integrating. It all goes full circle. Okay? Now, if you go on and plug this in, do a u squared here. U squared would be a squared tangent squared. Plug that in here, and it'd be a squared plus a squared tangent squared. Factor out an a squared, that gives you an a. 1 plus tangent squared is secant squared. The square root of secant squared is secant. So, full circle here, and then you go back to here, divide this by a, and secant is hypotenuse over adjacent. Hypotenuse over adjacent. Yes. So multiply that. Works. Okay? Involving this is, after a while you see, clearly a secant substitution because secant squared minus 1 is tangent squared. Okay? So that's going to be your substitution. Let u equal whatever the square root of that is times secant of this theta. There's your, before this was our u, and we said let u be some function of x that you found in your problem. Now this is what you're substituting. This is a new variable. It's part of the substitution. U is in the problem, not outside the problem. Okay? And if as soon as you have this substitution, divide by a, secant is u over a, secant is hypotenuse over adjacent, hypotenuse over adjacent. And that leaves the remaining side to be square root of this squared minus that squared, which is that. So everything just pans out really neatly. Okay? Now, they do have because cosine is positive here between these two, that's why we keep it between minus pi halves and pi halves. Down here, tangent is defined between minus pi halves and pi halves, but not with the equal sign. See, this you can include the equal sign, here you cannot, because tangent is not defined with either one of those. Here we have sort of another problem here, and most of the time this won't be a real problem, but it could be, so they mention it here. Remember that secant, which is what this is doing, always is greater than 1 or less than -1. Okay? So it's not sort of surprising that this thing, which is relates to the secant, has to be one value for u greater than a and another value for u less than a, because that's kind of the domain of secant to begin with. So here is where you are when theta is between 0 and pi halves. And if you think about the secant function, which is what you're dealing with, it does like this, okay? That from between 0 and pi halves can involve 0, but can't involve pi halves because it's undefined at pi halves. But when you're on the other side of it, the secant is positive here, but tangent is negative here. Because tangent does like this and secant does like this. So that's why, at least sort of qualitatively, you have to do the opposite of this to give you a positive value between, and then so you're going over here to pi halves to pi, not counting the pi halves because it's not defined there. So, again, a problematic. I was going back this way, they're going this way. Here is secant here, here is secant down here, so you have to flip this up. It's just a mess, okay? Most of the time, it will come out intuitively obvious, or else your problem won't go over there, okay? But it's something that probably you don't have to worry with unless you have to worry with, okay? So most of the time, you don't. All right, so let's try one. Oh, this doesn't look nearly as simple as what they were saying before. So what would be your guess? This is a sample of a constant minus something squared. Which one of those would this be? And this time, it's not something substituting for x, it's x substituting, well, it is something substituting for x. Not that this expression in x is going to be your variable. Okay? Now, if this had had an x in the numerator, a simple substitution would at least have a chance. Since there is an x up here, you have to go a trig substitution. So what will it be? Let x equal, second? Okay. Stick with sign, because it keeps things positive, okay? So it's going to be a sign, and the variable is my favorite angle of all time, theta, okay? It's equivalent to x in, linear things, theta in angular things. But we need some coefficient. Any guesses? When this was written before, this was written as a squared. So write the a. What would be the a? 3. There's your substitution. Now, I'm going to go 2 different directions with this, and I'm going to draw a picture at the same time. One thing we've got to do is then, because we've got to figure out what dx is. Okay, so what's dx? Okay, derivative of sine is positive cosine. 3 cosine theta. Remember, d's go with d's. Okay, so you have to put a d theta there. Another thing we're going to have is what x squared is. So let's, in 2 places. So what's x squared? What's x squared? If x is 3, okay, is what? 9 sine squared theta. Good. Don't get that done. Okay? Now, over here, I'm going to go a different direction. I just did the first step with the x squared, but I did it because of that one. Same thing works here. So let's next do what 9 minus x squared would be. That would be, I'm doing this in gory detail. If you don't need this much, you can skip some steps. 9 minus 9 sine squared theta. Okay, next thing I'm going to do is take a square root of that. Okay, and this would be, well, I can factor out a 9 there, and it's under a square root. And what's the square root of 9? 3. And what's left under there would be a 1 minus sine squared theta. Okay, and what's that? Cosine squared theta, and take the square root of that, and you get 3 cosine theta. Okay? Now, let's do our little triangle. Don't forget to do your little triangles. Okay? And it doesn't matter how pretty or ugly your triangle is, just as long as one's close to 90 degrees, and identify one angle as theta, and then go back to this thing and rewrite this as sine theta is equal to x over 3. Divide both sides by 3. So here's your theta. Sine theta is what? Opposite, which will be x over hypotenuse, which is 3. And what does that make the remaining side? The square root of 9 minus x squared, which is 3 cosine theta. Oh, man, this is just going in circles, isn't it? Because cosine theta is adjacent side over hypotenuse, which would be 3 cosine theta over, yeah. So that would be this thing over 3, yeah. So everything you need is here. Now let's start your substitution. The integral, what was your dx? Three cosine theta d theta over, what was your x squared? 9 sine squared theta. And what was your 9 minus x squared? 3 cosine theta. Okay. Whoa. All right. Obviously, the 3 cosine thetas can go away. All right. And that leaves us, this is a strange one. Why would they start us out with one this bizarre? 1 over 9, that can come out, we know that. Why would they start us out with one this strange? Okay?
You just want to make the sine squared theta like.
Yeah. I mean, yeah. What were you saying?
You just make it sine and you 2.
Okay, but rather than that, what is the 1 over sine? Cosecant. Okay. Cosecant squared theta d theta. Okay. Now, this is one you probably don't think of often. Is cosecant squared theta a perfect? Is that a derivative of anything? What about if that had been a secant squared theta? Is that a derivative of anything? What's that a derivative of? Tangent. So guess what? Cosecant is going to be except for a minus sign. Remember, the cos have the minus sign. So this is going to be minus cotangent theta. Okay. And then you put your plus c. Okay. So this one threw back to that. Seems like they just started you with one that didn't have that complication in it, but it wasn't that much of a complication, but it still was different, different enough. Now, I hope that's what they get. Frankly, I don't see an answer yet. Oh, okay. That's in terms of theta. We sort of need to get back to your x's, right? But why do you reckon I drew a little triangle up there? What is cotangent theta? I don't want you having to go through, let's see, theta is equal to inverse sine of x over 3. No, let's please not do that. Let's use our little triangle there and see what cotangent theta is there. See, I told you it's going to come in handy later. Maybe even earlier, but certainly later. There's your angle theta. There's all your sides. The x, the 3, and the square root of 9. Okay. So what is cotangent theta? Remind me. Adjacent over opposite. So that would be this over that. So instead of that, we will write minus 1/9. And what does it say? The square root of 9 minus x squared over x. Okay? Plus c. Okay. Now. Oh, and that's it. That's all they do. They write it a little differently. They put the 9 here in the quotient with the x, which is sort of a smart move, and just have the minus sign out in front. Okay. And that's exactly what they get. Minus the square root of 9 minus x squared over 9x plus c. Good deal. Any questions? Don't forget to do the triangles, especially at the end. They're going to come in so handy, rather than going back and trying to use this to rewrite theta in terms of an inverse sine. Use that, and things will be much, much, much cleaner. All right. Do I need to leave this up a little longer, or everybody got it? Okay. So let's see how they did it. First, note that the basic integration rules do not apply. In other words, you don't have a x in your numerator to go with the dx, so you can't do a normal u substitution, let u equal 9 minus x squared or something like that. Just don't have it, okay? So use a trig substitution. You should observe that that is of the form of a squared minus u squared, if that floats your boat. And you could have, as someone suggested, done a cosine substitution also, but it's just, sine is a little bit easier. You have fewer minus signs, that kind of stuff. So go with the sine substitution. That x equal a sine theta, which in this case is 3 sine theta, square root of 9 sine theta. Okay? Now, using differentiation and the triangle, do this. First, do your dx is 3 cosine theta d theta. This thing, which where you did your x squared, which they don't show here, but that is your 9 sine squared theta. Okay, and 9 minus that would then be 9 minus 9 sine squared theta. And this would be 9 times 1 minus sine squared theta. So square root of 9 is 3, square root of 1 minus sine squared is cosine squared, square root of that is cosine. So that all works out. And x squared, now they finally say it, is 9 sine squared theta, which I said early on. Okay, so here's your triangle. You get it from previous page that said let x equal 3 sine theta. So sine theta is x over 3, sine theta is opposite of our hypotenuse, so that makes that the x, that the 3. And then when you do the Pythagorean theorem, this comes out 9 minus x squared, which is exactly this, which is 3 cosine theta. Okay. Round and round and round we go. Okay. Now, they put this in here now, unfortunately. They already acting like they know what the answer is, and we don't know it yet. Let's go on and proceed here. The trigonometric substitution yields your dx is 3 cosine theta d theta. Your x squared is 9 sine squared theta. And your square root of that is 3 cosine theta. Those disappear. Okay? Just like they did for us. And that leaves us 1/9 of 1 over sine squared theta, d theta over sine squared theta. And they note that is 1/9 of cosecant squared theta, d theta, which happens to be the derivative of minus cotangent theta. So it's minus the antiderivative, that would be minus 1/9 cotangent theta plus c. But you don't want to leave it in thetas when the original problem was in x's, so then that's when this comes into play. If that's theta, cotangent theta is adjacent over opposite. So that would be this over that. And then that's what you put in for cotangent theta. Not doing cotangents of inverse sines or anything else. Just use your triangle. And that gives you minus 1/9 square root of 9 minus x squared over x plus c. Which then they put the 9 with the x. Just leave the minus out front. Good deal. Any questions? Pretty much like we did. Note that the triangle in figure 8-6 can be used to convert the thetas back to x's by that thing there. And just about every time you're going to want to use that. It's just so handy. Don't forget it. Don't ignore it. That's your square root of 9 minus x squared over x. All right. That was example 1. We've got 2, 3, and 4 all to do. Okay? So let's back up before we do that and do 2, 3, and 4. Any questions before we get going on? There is a little blurb at the bottom of that page 542 about technology using a computer algebra system. If you got one, by all means use it if you're interested. So, and they do some talking about inverse hyperbolic functions, which are some of my favorites of all time. I don't even like to mess with hyperbolic. So read it if it's of interest to you, or if your major uses those, you might want to follow it up. So here's example 2. Find this integral. Integral of dx over the square root of 4x squared plus 1. All right. Can you think of any likely method to solve that, to calculate that integral? No substitution, no, that's just not one that's going to come out handy. But it does have that radical in it, and it does have one of the forms that we have been talking about. So what would be your substitution? Second? Okay. It will be tangent, but tangent of what? Okay. Here is where it gets a little tricky. Notice here, we were okay with a 1 or an a squared here. But this was always u squared before, wasn't it? What would be your u if this is u squared? 2x. That's where you do a little bit different here. Let 2x equal what you were saying, the the A, which is 1, times the tangent of theta. There is your substitution. A little bit bizarre, right? So what's then your then that follows that? What was usually our next step? Then 2dx is equal to secant squared theta. Derivative of tangent is secant squared. Okay? So dx would be secant squared theta over 2. Oh, I forgot my d theta. Always have a d with a d. Okay. Now, that's carrying that out. Let's go a different direction here. Let's do our 2x squared, which is 4x squared. That would be tangent squared theta, right? Okay. Plus 1. That would be what? Trig identity. I mean Pythagorean identity. Secant squared theta. Okay? And then you take a square root of that, which is what you're doing here. And I should have written in 2x in parentheses squared plus 1. And that would have been this. That would be the square root of that. And this would be secant theta. All right. One other thing should we do? Little triangle. Don't forget your little triangles. They're so handy. Make this be your angle theta. And from our very first thing, tangent theta, well, I don't have to write it again. Tangent theta is 2x. I don't see a denominator there, so what can we do? Over 1. And what is tangent theta? Is what? Opposite over, so that would be 2x over 1. And then by Pythagorean theorem, what's your hypotenuse? 4x squared plus 1, which is exactly what we have down there. Okay? We'll come back and do the rest of that later. Okay. So let's substitute in our substitution. The integral, your dx was, I'm going to bring the 1/2 out front, secant squared theta, d theta, with the 1/2 out front, over, what's the square root of 4? I should have done that. This is our square root of 4x squared plus 1. That was secant theta. Right? Well, secant theta and secant squared theta. Secant theta times. Does anyone remember what the integral of secant theta was? That was one of those kind of weird ones. That's the derivative of it. The antiderivative of it. If you have a chart that you can go to, some book that you have, the integral of secant u du is the log of secant u plus tangent u plus c. So this is 1/2 the natural log of secant theta plus tangent theta plus c. Now, that's in terms of theta. It looks really neat, but we need it in terms of x. So how in the world can we do this? Easier than that. Use your triangle. What is secant theta? Hypotenuse over, second, adjacent. So that would be, so this will be 1/2 the natural log of, and your hypotenuse is the square root of 4x squared plus 1 over adjacent, which is 1. Ha! That's pretty nice. Plus, and what is tangent theta? 2x plus c. There you have it. Oh, isn't that triangle nice? You think it's sort of a pain in the neck having to draw every time? No, it's not. So easy, and it should get you where you need to go. So what we have here is 1/2 the natural log of the square root of 4x squared plus 1 plus 2x plus c. Got it. Okay. They mention here you can use these same substitutions. That's why I wondered why they were limiting it to square roots to begin with. They didn't have to. Anytime you see one of those forms, 4x squared plus 1, just by itself, in a denominator. Certainly in the numerator you can deal with that straightforwardly. But, anywhere else, or raised to any other power. It didn't have to be to the 1/2 power or the negative 1/2 power. It could be to any, especially any half power. Okay? And that's what we're going to do next in example 3, which is also located at larsoncalculus.com. If you go there, you can see an interactive version of that type of an example with a honcho interacting with you. Okay? So this time we're going to do the integral of dx. Boy, whenever you see that, just a naked dx up there on the top, you know you got problems, okay? X squared plus 1 to the 3/2 power. Okay. What comes to mind? Second? Tangent. Okay, so what would you say? Let? What? Help me. X, yeah, X equal your tangent theta. Now, theta is my favorite. If you like something else to call your angles, you can call them anything. Don't call them X. Don't call them suit. No, that's a different thing. Okay. Then, what's your next step usually? Dx is equal to secant squared theta d theta. Don't forget your d's. These go together. Okay. Now, if x is tangent theta, what would be x squared? This is going a different direction here. X squared would equal tangent squared theta. Okay, and x squared plus 1 would be tangent squared theta plus 1, right? And then if you raise this to the 3/2 power, you could raise this to the 3/2 power, and what would that be? What is tangent squared theta plus 1? Secant squared theta. Okay, raised to the 3/2 power. Well, guess what? A half power takes care of a square, doesn't it? Okay, so those go away. So this leaves you with a secant cubed theta. Right? All right, let's see what that leaves us with. Here is the integral. Your dx is secant squared theta. Oh, one thing we didn't do, did we? Our little triangle. Don't forget your little triangles. Okay? There's your theta. Let's go back here and, oh, it's already written for us. Tangent theta is x over what? 1. Okay, so if that's your theta, what is your x? I mean, what's tangent theta? Opposite x over adjacent 1. And what does that leave your numerator, I mean your hypotenuse to be? X squared plus 1. Okay, so there's your handy dandy little triangle, and we're happy with that. So now we've written our dx as secant squared theta d theta over, and our x squared plus 1 to the 3 has power. X squared plus 1 to the 3 has power is secant cubed. Everybody see that? All right. Now this will wipe out those, right? You have secant squared in the numerator, secant cubed in the denominator, leaves you 1 over secant squared. Anyone know, 1 over secant. Anyone have a recollection about what 1 over secant is? Cosine. Cosine theta d theta. You know, I'm coming close to being able to do that myself. What is that? That's sine theta plus c. But we don't want to leave it in terms of sine, do we? Or in terms of theta. We want it in terms of x. So where do we go to get that? Your triangle, of course. And what is sine x? I mean sine theta? X over the square root of x squared plus 1 plus c. Can it be that easy? I hope so. Yes. X over the square root of x squared plus 1 plus c. And that started out being, oh my goodness, cubes, 3 has power? No, we haven't done anything like that. But just use the procedure, and a lot of times it'll work out. We hope it will anyway. Except on the test. Okay, no, I didn't say that, did I? All right. That was example 3. I think we've still got example 4 to go, don't we? How are we doing? Oh, yes, we've got plenty of time. So let's do example 4. Any questions before I wipe this out? Everybody got it? All right. Example 4. Whoa. Definite integral. Going from root 3 to 2. What nice limits. Okay. Square root of x squared minus 3 divided by x dx. Oh my goodness. Is this not a mess? Where would you begin? Anybody? Well, it's not a sine because that has to be the constant minus the square. Secant, okay. Let x equal what? Okay, it's certainly going to have a secant theta in it. Got to have something else though. Not quite 3, the square root of 3, because that has to be the square of it, right? Okay, so that's that. Then dx is equal to square root of 3 and what? Not quite. Tangent's in there. Secant theta, tangent theta. Remember, that's the weird one. And then, of course, you got to have your d theta, right? Root 3 secant theta tangent theta. The derivative of a secant is secant tangent. Derivative of cosecant is minus cosecant cotangent. Okay. So there is what we've done along that line of thought. Let's continue up here. Now that is a square there. That's a pretty ugly 2, isn't it? Let me see if I can make it a little bit clearer. I'll wipe it all out. That will make it clearer. Okay. Now, according to what we just did, what is, if that's x, what's x squared? Second, 3 secant squared theta. Oh, I didn't write x squared is equal to 3 secant squared theta. Okay? And then subtract the 3 from that. X squared minus 3 would be 3 secant squared theta minus 3. Okay? And then the square root of this would be the square root of that, which would be the square root of 3 times the square root, I just pulled out the square root of 3, the square root of secant squared theta minus 1, which would be square root of 3 times, second, that's tangent theta. Because secant squared theta minus 1 is tangent squared theta, and the square root of that would be that. Okay? One other little thing to do, what would that be? Get a little triangle. Okay? And this said that x is equal to root 3 secant theta. That means secant theta is equal to x over root 3. That's all we need to fill in our gaps here. Once we identify what our theta is, what is secant theta? Hypotenuse, which that would now be my x, over adjacent, which now has to be root 3. So what does that make our opposite side? Wouldn't that be that? Which is exactly what we have here. Okay. Interesting, but true. Okay. Now, let's go back to our integral. But, big but, okay? When x is equal to 3, right? No, I mean square root of 3. Then what is our theta going to be equal? Because we're changing the d thetas here, okay? Because I'll go on and write that in. You know that's going to be, well, let's go on and not do that until later. What is the square root of x squared minus 3? The square root of 3 times the tangent of theta. Okay? What is x? Okay? So that root 3 is going to wipe that one out, and this will be secant theta. And what's your dx? Root 3. So what we're going to happen there, we're going to put back in a root 3. So we'll leave it back like that. It's nice to have an erasable thing here. Okay, and that would be root 3 secant theta tangent theta d theta. But the secants go out, and that leaves you root 3 times the integral of tangent squared theta. Okay. Now, what I've left off doing is changing our variables. Okay? So this is your x, or those things. So when x is equal to root 3, Put a root 3 in here, and so divide by root 3, right? And that gives you a 1. And when is secant theta equal to 1? What value of theta is secant theta equal to 1? Okay, secant theta is 1 over cosine theta. What value for theta would be 1? So 0 when theta equals 0. So this lower limit becomes a 0. Now the upper limit, okay? When x is 2, 2 is equal to root 3 secant theta. So 2 over root 3 would be secant theta. What value would that be? Okay, let me write it down for you. That 2 over root 3 is equal to secant theta. And again, I don't think in terms of secant theta very well, so I want to change that to 1 over cosine. So that would make cosine theta equal to square root of 3 over 2. And at what angle theta would that be true? Second? Pi over 6, you got it. So this would be pi 6. And by the way, thetas are angles, and these are very reasonable angle values. Okay? So that makes me feel warm and fuzzy inside, or somewhere. Okay? So 0 to pi 6. Okay. Now, all that seemed to be doing quite well until we got to tangent squared theta. Anyone remember what we do with that? If nothing else, think that that's the Pythagorean theorem, identity. What would that be? Secant squared minus 1. Let's see if that helps any. So this will be a root 3 times the integral from 0 to pi 6 of secant squared theta minus 1 d theta. That's what you said, right? Which would be root 3 times the integral. I'm going to put this a big thing. 0 to pi 6 of secant squared theta d theta minus the integral from 0 to pi 6 of d theta. Probably didn't have to do that, but I thought I would. Ooh, I need some room, so let's write this as square root of 3. What's the antiderivative of secant squared theta? Tangent theta. Oh, we've got these down, don't we? Tangent theta evaluated from 0 to pi 6. Okay, we'll come back to that later. Minus, oh, that's a hard one. What's that? Pi 6. Is theta evaluated from 0 to pi 6. That's going to be pi 6. Minus, okay. All that is multiplied by that. Now, this may take a little bit of memory here. Remember what the tangent of pi 6 is? Does anyone remember? I'm going to do a different little triangle. Whoops, that's not very representative. Okay. Pi 6, remember, is a pretty small angle. Okay. And this is 1 to the square root of 3. Remember that? Sure. For 30 degrees. Okay. What's the tangent of that? 1 over root 3. Right. So this will be a root 3 times a 1 over root 3. And how about when I subtract, what's tangent of 0? 0, okay, that's gone. Minus pi 6. And this looks like it's going to be 1 minus pi over 6. Pi over 6 is not far from 1/2, a little bit more than 1/2. This is going to be something a little bit less than 1/2, I think. Anyone got a, oh, please don't tell me that.
It's like 0.48.
I messed something up here. Oh, wait. No, I mean, yeah. I see where I messed it up. This has a root 3. Remember here that I said pull the root 3 out? It's in front of everything. When I did this integral here, I just put pi 6. It has the root 3 times pi 6. So this would be 1 minus root 3 pi 6. So that's a completely different story. Root 3 is something less than 2. 2 times 3 is 6. Almost seems like that's going to be great, too great, but it's going to be an awfully small number. What is it? 931. Yep, that's what they got to. All right. Forgot to carry my root 3 over. Okay. So sure enough, there it is. And again, a very small number. And on this one, I don't know, we hardly used our triangle at all, did we? Because we didn't have to convert back and forth. We just changed our limits and flew. But they said you could go back to the variable, and they showed you how to do that, and it comes out the same thing, but it's a lot messier process. And they showed you something else there. Another way to do it. So I'll let you take a look at all those if you'd like. Okay. That finished 4. Any questions? Erasa, can we move on? Okay. All right. Trigonometric substitutions can be used to find the 3 integrals listed in the next theorem. These are the ones we've been dealing with. And these integrals will be encountered several times. That's a promise or a threat. Okay. Now, most of the time these showed up in denominators or mixed up otherwise. They can be in the numerator. Okay? Now, if they're in the numerator, things are probably going to work out a bit more strangely. And they certainly appear to from these 3 things. Now, why they didn't have you do these rather than just write them out for you, I'm not sure. Because we could have done it. It would have been messy, so maybe we're thanking them that they didn't make us do them. But they say you're going to encounter it several times, so here they are. Now, most of the time, you're going to have a table. You look up in the table, and those forms will show up, and this is what they're going to give you. Okay? So, thank you for not making us go through all the agony of doing that. There's no really clear aha pattern in this at all. Okay? The only thing to note is that this shows up in the first term, but not in the next. This shows up in the first term, but not in the next. This shows up in the first term. Oh, these 2 show up later on inside a log there, which is a bizarre place to do it, flat out. But you never jump from this over here to one of these others over there. They always pretty much carries that same form. But not worth memorizing in my mind. Look it up if you need it. Okay. They have two applications. I think they're probably only going to show one. They may show them both, but let's see how much time we got. Let's see if we can do it. Find the arc length of the graph of f of x is equal 1/2 x squared from 0 to 1. Okay? X equals 0 to 1. Well, obviously the y is going from 0 to 1/2 then. So there it is. A vertical shrink by a factor of 1/2. We want to know the arc length between those two values. Now, does anyone recall what your arc length formula is? Say again?
Square root of 1 plus the derivative squared.
Did you say f prime squared?
Yes.
Okay. And that would be the integral of that dx. That's what you meant? Okay. And since x's are going from 0 to 1. Okay? So what's the first thing you got to do? Take your derivative. So what's your f prime of x? X. Okay? And what's that f prime of x squared? X squared. Okay? So that gives you the integral from 0 to 1 of the square root of 1 plus x squared dx. Now, remember back when we were doing these, I said they come up with all kinds of convoluted type functions that you can actually take a derivative, square it, add 1 to it, and take a square root and get something integrable. Well, guess what? Now that we've got another tool in our belt, that opens us up to a lot more formulas, because that is one just like they showed on the previous page, wasn't it? Okay? So, let's go back to the previous page and see what that antiderivative is. Well, I won't call it that. The 1 plus square root of 1 plus x squared. That's this one down here, number 3. And what a mess, but doable. In this case, this is a 1 and this is an x. Okay? So, 1/2 parentheses x times that very thing, okay, plus 1 squared, 1, okay, log absolute value of 1 plus, no, x plus that thing, okay, evaluated from 0 to 1. Okay? Don't go back and reinvent the wheel. They told you you're going to use it. There it is. Use it. I hope I got everything right, flipping back and forth. Okay? Now, I'm going to write down the 1/2. Yeah. Okay. Yeah. Okay. Now, let's plug and chug. For the 1, that would be 1 times the square root of 2, right? Everybody see it? Plus the log of, absolute value of, 1 plus the square root of 2. Now, since that's positive, I don't need absolute value bars anymore. Okay? Now we're going to subtract your lower limit. Plugging in for x, you get a 0 from the first term. Plugging in a 0 on the next term, you get 0 plus the square root of 1. Square root of 1 is 1. The log of 1 is 0. So you get nothing from that second one. So it looks like this is what you got. Root 2 plus the natural log of 1 plus root 2 over 2. They put 1/2 in front, okay. Root 2 log of root 2 plus 1. And they figure it out and give up with an answer of about, anyone do it? 1.1, they put 1.148. Yeah, rounded to 1.15. How they do significant digits is beyond me, but anyway, that's what they got. All right, that's how we did it. Let's see if they did it any differently. Okay. Refer to the arc length formula, which Anthony knew right off the top. S is equal to the integral from 0 to 1 of square root of 1 plus f prime squared dx. So, without showing you, over here on the right, they say f prime is equal to x, so that would be the integral from 0 to 1 of 1 plus x squared dx. And they jump to secant squared theta, which we could have done. Okay? And I guess we should have done. But I used the formula they gave. So let's do that. It looks like so much fun. I have a feeling it won't be. Yeah, let's try it. How did they get there? This trig substitution is which one? Is what? Tangent x. Okay. Then equal secant what? Squared x dx. Let's go this way with it and do what x squared is. Tangent squared x. And add 1 to it. 1 plus tangent squared x. And right there, I think I would say let that equal secant squared x. Wouldn't that be okay? Because you know 1 plus tangent squared x is secant squared x. And then take the square root of this, which is the square root of this, which is the square root of this, and that is equal to secant theta. Okay? And that's how they go, jump right to the integral from 0 to 1 of this thing is secant theta, and dx is secant squared theta, d theta. So that's how they got to the integral from 0 to 1 of secant cubed theta d theta. Now, anyone remember what we do with that one?
Change the balance.
Second?
Change the balance on the interval.
I couldn't hear you.
We have to change the 0.
Oh, yeah, we need to change our things. I'm sorry. When we need to change it here too, so let's change. Okay. We're kind of running out of time. Let's see what would it be when x equal 0. What is this? Is a theta here. Y'all are letting me do all sorts of messy things here. These are thetas. I finally got the theta there, and this is a theta here. I don't know. Okay. When x is equal to 0, what is theta? 0. Okay. When x is equal to 1, what's theta? Pi fourths. So 0 to pi fourths. All right. Now, are we going to have time to do secant cubed theta? I think this is the reason they gave us the other one. But if you'll go back to secant cubed theta, to our rules, where were our rules? In the trig substitution, secant and tangent, number 4 on page, well, if you don't have it, when the integral is of the form secant m theta d mx dx, where m is odd and positive, use integration by parts. Okay, so that's where we would have to go from there, and it's not bad, but it is lengthy. Okay, what do you think your by parts would be here? We'll just set it up. I don't think we're going to have time to do it. Let u equal, and now we're going back to u's, equal which? Okay. I think that's going to be the secant theta, don't you think? And dv equal secant squared theta d theta. Any reason why? Because that is a perfect derivative of tangent. Okay, so then next step down here, du is equal to, say again, secant theta tangent theta d theta. That's why I didn't want to go this route. And v would be tangent theta. All right. Then your, and we haven't even done our triangle yet. We need to do that because that's going to be showing up here. But we're running out of time, aren't we? Okay. Now, do you want to finish this one at home? Okay. Or do you want to pick up with this when we come back? You'll just have to remember to tell me where you left off if you got good notes. Want to finish this one and come back next Monday? Okay. So it's going to be here. Wait, that's not what I want to do. Let me end this.